Rahim. Today we are going to do low power circuits, and these slides are adapted from Frank Seal Torres. Okay, so I first go through the introduction, power reduction on the gate level, architectural level, and then algorithm level and system level. Okay, so what are the problems in power dissipation? So current problems in power is that power is continuously increasing due to high performance requirements. Our circuits are very complex, and we now increasingly demand that the chip has to complete a lot of functions, and this causes the functions to be very complex and increases the power dissipation of technical devices. So before this, in the past 20 years, most foundries were racing to shrink the size of devices, but then they found out that there is a limit to the amount they can shrink the size of the circuit, because we are almost reaching the atomic level. So now, what is the problem when we have such small devices is that the power density in a specific area, in the small area of the chip, is very high. So this is the main problem of today's chip, and this is what the engineers are focusing on. So they are currently working to reduce power dissipation in chips. So when there is a very large or very high power dissipation, it reduces the functionality of your devices. It causes the device to consume more power and more battery power, and when you have to have larger batteries, you have reduced mobility, and power dissipation also requires a lot of cooling. So there are many dedicated chips used for cooling. This power consumption also increase the operational cost, because there is additional circuitry that is required to reduce the temperature of the chip, and when the chip gets heated up, there is reduced reliability. The chip tends to malfunction quicker. So what about power dissipation in your laptops or notebooks? The devices that causes a lot of consumption of power is in the processing. For example, the digital signal processors, the memories, the dedicated chips for communication, the WLAN and the Ethernet, the peripherals, the disk, and the display also all consumes power. Okay, so what are the examples for energy dissipation? This is the example of the breakdown of energy dissipation in a notebook. So most of the power consumption is due to the display, and then the next thing that consumes a lot of power is the CPU or memory, and then next is the hard drive or disk, and the network, and the rest remaining goes to other circuits. Okay, for a personal device, also the display takes 30% of the power, and the next one is the audio, and then the RAM, and all the other communication. Okay, so this is an example of how the power is distributed across a chip. As you can see, that the power density is not uniform across the entire chip. There will be areas which are hot spots, and this is because silicon is not a good heat conductor. So certain areas which are switching very quickly, they will consume more power. So this causes certain areas to have higher temperature than the others. And as you can see here, the on-die or on-chip temperature can go up to very high temperatures, above the boiling point of water, greater than 100 degrees. So because of this high temperature, it causes impact on packaging and cooling. So what are the key points of measuring power? So power can be defined as the amount of energy given for a unit of time, and it usually measured in watts or kilowatts. Okay, so power can be categorized into two: either average power, which is the average amount of energy consumed per unit time, or instantaneous power, which is the energy consumed at a specific instant or when the time unit goes to zero. Okay, energy is the ability to measure for a system to do work or produce change. So if you multiply power with time, you can get energy. Energy units are in joules or kilowatt hour. Okay, so like I mentioned earlier, electrical power can be defined as instantaneous power, and this is simply P equals to V times I, voltage times current, right? So the voltage specifically is the potential difference or the voltage drop across a specific device, and the current is the current passing through that specific device. Okay, so for energy, you just simply multiply the power with time. So E equals to P power times T, or the duration. Okay, you can also equate it as power times delay.